Okay, so we are now starting the shorter presentations of shorter submissions to Augmented Human 2021. And the first presentation is titled Wearable Augmented Reality Application for Training and Maintenance of Reclosers. And this one is presented by, let me check again. I have the, so this one is wearable. So it's Arthur Batos, right? Who is presenting this one? I guess, yes.
Yeah, this is me.
Okay, good. So I will give you the, let me give you the right to present. Yeah. And where is the Arthur Batos? Where are you here? Okay. Yes, now you are co-host, so you can share your presentation. So this one is a bit shorter, so you have around like 8 minutes, then a few questions afterwards. The floor is yours.
Hello, everyone. My name is Arthur, and I'm here to present you our short paper describing Coppelia, an ongoing project in the electrical distribution industry. The project started when Copel, a major distribution company in Brazil, reported some issues they have in their current process. It works as follows. First, someone calls the operators stating a problem like, I don't have energy in my neighborhood, or something like this. And the operators, they send a team of 2 generalist electricians to register the problem and hopefully fix it. And sometimes they can't fix the issue because they don't have the knowledge required for this. So in the case of problems related to reclosers, which are devices like this one here, which protects the energy grid from power surges, they need to call specialists for further assistance. However, those specialists are not always available, and sending multiple teams to work in the same problem may impact Copel's budget in a long term. Furthermore, we also had to consider challenges such as the difficulty many companies have to adapt their traditional processes to new technologies such as AR, and find workers who are willing to use these technologies. We also had to consider the safety measures necessary during the pandemic when planning a solution. And this is what we did. To understand our users' needs, we performed an UX design survey. And from the survey, we identified a series of features and compared our proposed solution to other solutions available in the market. We started prototyping our own application, and by the time of this short paper's writing, we were still iterating over user testing. So let's talk about the application itself. Coppelia runs in a smart glass, which is a device like this one in the picture. And users can interact with the application hands-free via voice commands. It also has audio feedback and provides a series of safety measures for industry work. We proposed features that can be used both for generalists if they need assistance and specialists when they need training. And a few of those features are the detection of recloser models. We use a neural network for this. In the image here, users point the camera to a recloser. We have a set of reference pictures, and the applications asks if the detected recloser is really correct. We also provide instructions about maintenance of reclosers, and each instruction is accompanied by animated 3D models in augmented reality. In this picture here, we can see an example. It's all in Portuguese because it's still in experimental phase, so it's not internationalized. But this is the battery replacement procedure, and it's showing instructions about how to disconnect some cables and the animation points where these cables are located, the direction they should be unplugged, and so on. We also have other minor features, such as video instructions when the augmented reality models can't be used for any reason. And we also provide a virtual scenery for cases where users don't want to use the camera for any other reason, but still want to see the animated models. We provide access to documentation and also video calls. And this here is just a picture showing how we tested the application remotely. We had the smart glass connected to a computer. We used a software that mirrors the screen users could see in the smart glass. And we also provided photos of the recloser if the user doesn't have a real model nearby. And these are just preliminary results. So far, the application was well received, but the experience was still not good enough. Our UI was not adapted for the tiny screen, so elements placed around the corners could not be visible sometimes because during everyday use, the screen moves and we have to constantly readjust it. Also, in some screens that required the camera, sometimes the UI was obstructing it. So users couldn't properly see animated, AR animated animations, sometimes because they were behind a button, for example. We also noted some things like the audio feedback, which would greatly increase the overall experience. And we also had comments that couldn't be activated properly because they were in English, for example, and the system was configured to Portuguese. So, for example, in this word here, we expected to activate saying trip saver, but since the system was configured to Portuguese, we could only activate spelling this in Portuguese, something like trip saver, which doesn't make sense. We also had some commands that meant something in a screen, but meant something else in another screen. So we had to change it because it was confusing. And finally, the documents provided by the client were made for PC. So users who tried to read them in the smart glass screen didn't have a pleasant experience. From this single test, we noticed that most issues were related to our own bias in designing interfaces for traditional screens. Our next steps would be redesigning and retesting the interface based on those findings. Thank you very much. I hope you enjoyed this presentation. And if you have any question, please let me know.
Yes, thank you. So do we have a question in the audience? If not, I have one question. So, you know, this kind of application may have some risks and may be dangerous in case of electricity shock and so on. So in case of an accident, you know, like an accident happens when the system is used. So who is responsible? because it's a bit like in smart cars, you know, like autonomous cars. We don't, sometimes we don't know who is responsible. Here, maybe the system, or we don't know if the system has given bad instructions. But anyway, there is an accident. So have you already discussed this kind of questions with your partners?
They have a prior training about how to wear the smart glass and also to perform the operation safely. But I think in the case of an accident, it's their responsibility.
So you have signed a contract. I mean, this is clearly stated in the project that you had with them.
Yes, our contract states we are only responsible for the application. The hardware itself, it's by Propel.
Okay. Okay. Thanks for your contribution. Now we have to move to the next short presentation. Thank you.
Thank you very much.
Yeah. The next one is XLAMB, wearable robot arm with storable and extendable mechanism. So I believe Shogo Yoshida is presenting it. Is it right?
Okay.
I will give you the co-host to share your screen.
Okay.
Now you are co-host.
Okay. Just a second.
So the floor is yours. You can.
I cannot share my screen.
So you are. It's not Shogo present. It's Ziyu.
Ding. Yeah. It's me. Ding.
Okay. Okay. Shogo is. You had a double co-authoring. He co-authored maybe another paper, right? Okay. So I will give you the co-host, right?
Okay. Thank you.
Okay.
Yes, thank you. Okay, please wait a second. Oh, can you see my screen now?
Yes, it's okay. The floor is yours.
Okay, thank you. Good afternoon, everyone. My name is Ding, and I come from Japan's Advanced Institute of Science and Technology. And today, I would like to share you with XLAMB. This is a wearable robot arm with storable and extendable mechanisms. And first of all, I would like to talk about our motivation. So in our daily life, we may meet with some difficulties such as our hands are full, or sometimes you just do not want to contact with something directly, or something is too far to get. So in these kinds of situations, if we have a third arm that can support us, we could live a better life with more convenience. So our purpose is to develop a wearable robot arm that could support our daily lives. And then to achieve our goal, we refer to some previous works in both HCI and robotics field. For the former, we focus on the wearable robot arms that can support the user as a third arm. And for the latter, we aim to improve the wearable robot arm with storable and extendable mechanisms. The reason for why we apply such kind of mechanisms is that we found most existing wearable robot arms are with huge volumes. So when the users are wearing it but not using it, they may feel a little bit inconvenient. So based on that, we decided to develop a kind of wearable robot arm that is more user-friendly. So then before we started to make our prototype, we conducted a pilot study to verify our design method. We invited 14 participants to join our experiment and requested them to imagine their own ideal wearable robot arm. The questionnaire consists of some multiple choice quizzes in 4 main aspects: the application scenarios, the important features, the ideal body part to mount it, and the ideal reachable length. And according to the result of the questionnaire, the ideal image of the wearable robot arm is similar to what we supposed. And it could be simply described as for application scenarios, it should be used to enhance the user's capability in manual labor, and it should have some features such as storability, extendability, operability, and so on. And the upper arm is considered as an ideal body part to mount, and the ideal reachable length should be about 1 to 1.5 times long, the distance from the user's elbow to the fingertip. And on this page, here comes our prototype X-Limb. There are 3 main features which are shown in the right side. The first one is the lightweight design. Our prototype is just 687 grams weight, and this could help to lower the burden on the users and motors. And the second one is the storable mechanism. The user could store it in compact size when they are not using it. And the third one is the extendable mechanism. The user could also extend the reachable range if it is necessary. In this page, here are some further details about the structure. Some main parts are marked as blue. They are first the base. The user will mount this part to their upper arm, and then the extendable mechanism, which I have already introduced in previous slide, and then gripper, which is used to grab some objects, and finally is the base motor. This is also considered as an important part because it has to endure the whole weight of the device. And then as a prototype, it has 3 degrees of freedom. They are opening and closing, and extension and rotation. To make it clear that how these joints move, we also prepared some videos, so please have a look at it. Okay, and next, about the extendable mechanism, I would like to make some further explanation. This mechanism consists of 2 main parts. The first one is the mechanism itself, and the movement has already shown in previous slide. We have already know about it. And the second part is an external supporter. I'm showing it in the blue color. And it's obviously that this kind of mechanism, it is weak in this vertical direction. So to make sure it is strong enough, when we're using it, we add an external supporter. In this page, I'm going to talk about the core method about our storable mechanism. As we know, the torque exerted on the user's shoulder joint and the base motor is affected by the distance and the force. However, the force here, namely the weight of the whole device, is not changeable. So we decide to reduce the burden by reduce the distance. By applying the storable mechanism, we can see that under the folding state, the distance is reduced compared with the distance in unfolding state. So when it is not necessary, just switch our device into the folding state will help to reduce the burden on the users. And in the next following 2 pages, here are 2 simple applications. The first one is the user trying to pass an object from one side to his hand on the other side. Okay. The next one is the user trying to turn off the light with our wearable robot arm. Okay, thank you. Then to evaluate the effectiveness of our device, we conducted a user study by a questionnaire. So participants are asked to give scores on some characteristics such as storability, extendability, or convenience. And we also provided some scenarios for them before they give scores. They just need to achieve some simple goals, such as move some small objects to somewhere, and then they could control our robot arm freely just for further experience. And here are the results of the questionnaire. After analyzing the statistics, we could say that our prototype is comfortable and useful with the storable and extendable functions. And especially by contrasting the experience and their folding and unfolding state, respectively, the score of convenience is increased by about 20%. And in addition, the participants also give some feedbacks on how to improve our prototype, such as to make the extendable mechanism stronger in order to lift heavier objects, and so on. Finally, the conclusion. In this research, we developed a wearable robot arm with storability and extendability for human augmentation. And we conducted a user study to evaluate our device, and the results shows that we have achieved our initial goals to make an ideal wearable robot arm. The result shows our extendable mechanism ensures a necessary working space for daily activities, and it helps to maintain a compact size when it is not being used. Then our storable mechanism and the lightweight design decrease the burden on users, which makes it possible for long-time usage. And in the future, we are going to concentrate more on the control system to make it more intelligent for users. And that's all for today's presentation. Thank you for kind listening, and I'm glad with any questions or comments. Thank you.
Thanks a lot for your presentation. Yes, we have a number of questions. Let's see. Okay, so did you consider that it could be used for amputees or people who have a disability in the upper arm?
Yes, we had considered such kind of situations. In fact, in present stage, we are trying to develop to using a EMG sensor, which could detect the electronic signals of your muscles. By using it, we are trying to recognize the user's gesture, and by using the gesture to control the wearable robot arm. But for the situation, if the user has some physical disabilities, especially the disabilities on his arm, I don't think it's a good choice to use the EMG sensor to control it. So maybe using brain waves or other control system is a better choice.
Okay.
Thank you.
Okay, so we have several questions, but we don't have time for too many. I just wanted to underline, like, so because you said you studied to reduce the burden, but it was more from my understanding, to reduce the burden on the technical device. Do you plan to do more longer studies of the the medical aspect of your device and the burden that would be put on the human body? Because I think this is this kind of research may impact a lot in the long term, even if it's if you have it for a few days, there is no impact. But when you have such device or such posture, such position for months and years, then it can create a lot of stress on your skeleton. And so anyway, so have you planned to if you continue to develop some extra arms and other augmented device? Yes, because I think this is important. Even when we work on computers or when we work on smartphones, people started to have pain in the neck, due to the position of their head. And here the arm might, even if it's lighter, that might create a lot of stress on the body. So have you considered to work with some medical people to study that?
Yes, of course, that's an interesting field. But I think in present stage, the biggest issue is to find out a proper way to control it, especially for just like what you said, for medical use, you need to consider how those people with some physical problems, for them, how to control it easily. So expect, besides the EMG sensor, we would like to try some other control theories, and if we could find a proper one, then it's time to decide to make further research in the medical field.
Okay.
Thank you.
Thanks a lot for your presentation. So now we are moving to the next one.
Okay. Thank you.
Yes, thank you. So the next one is called Navi Choker, augmented pressure sensation via pneumatic actuator. And here, so who is presenting, like Shogo or?
Yes.
Yes, okay. So I think I gave you already the co-host, so you can already share.
Okay.
The floor is yours.
Please wait. Can you see my presentation?
Yes, it's okay. Thank you.
Okay. Okay. Hi, everyone. I'm Shogo Yoshida. In this study, we introduced Navi Choker, a walking direction presentation system using a small pneumatic actuator. Virtual space, augmented reality, and real-world interaction provide users with a variety of experience using not only visual, but also haptic technology. It is widely used in entertainment, daily life, and simulations. TactSuits is a typical example of a consumer device that uses haptic technology. It is a vest that converts the upper part of the body and contains a number of motors. The motors can act independently and interact with the application. For example, when the user's body is shocked in the VR world, the users can feel some shocked same place in the real world. In this way, haptic technology is familiar to us all and everyone can experience it. This type of haptic technology is classified as a form of human augmentation. There's a lot of research on human augmentation. For example, the installation of automatic vent on crosses to control body temperature, and the application of electrical signals to the arm to feel the weight of virtual objects. In report, the device that much loaders installed can be used as a navigation device by utilizing the resistance. However, the user cannot use the device in a small space due to the large size of the device. Also, it is not safe to handle a large device without being able to see the surroundings, as it is assumed that a headset is one. So the device is not practical use in real life. The fourth jacket is a device that uses air pressure to provide haptic feedback to the user. In this device, the actuators on the inside of the jacket can act independently and can be used in conjunction with the VR applications to reproduce the sensation of being wrapped by a snake or hit by a ball. However, this device can only be used in a limited space because it requires a large device to operate. In addition, the user cannot use easily because its mechanism is very complicated. Therefore, we developed the NaviChoker, a small haptic device that can be used anywhere. In NaviChoker, 4 pneumatic actuators made attached to the inside of the choker and inflated to present tactile sensation. This is the system configuration of the NaviChoker. The device consists of a choker, pneumatic actuators, a silicon tube, and a syringe. A silicon tube connected with the syringe is attached to the actuator. By manipulating the syringe, the actuator can be inflated. The actuator is made of 0.08 millimeter polyethylene film. Making a pneumatic actuator is very simple. First, draw a 1.5 centimeter by 2.0 centimeter rectangle on a film. Then cover the film with a cookie sheet and place the rectangle with a solenoid iron. Finally, cut it out with scissors. This is how it works. Before implement user study, we verify the relationship between the presentation of pressure and the ejection felt by the user. We present a total of 15 tactile patterns to 7 participants. After that, the users records the direction in which the user feels. After collecting the data, we decided to use the pressure pattern for the user study. In the user study, 9 participants evaluated the system. As an experimental procedure, the user is guided to the destination only by the pressure presentation by the device. We didn't inform the user of the destination and made sure that the user had never been to the destination before. As shown in the video, the NaviChoker guides the user to the destination. The user is presented with pressure to start walking, change direction, and finish walking. In this experiment, we use the Wizard of Oz method, and the actuators were activated manually. As a result, 8 participants were able to reach their destination only by pressure presentation. It suggests that Navichoka can be used as a navigation system. However, one participant got lost in the vicinity of the destination. It was because the finished walking signal was perceived as retreat. So it is need to more research for appropriate pressure intensity and presentation position. After the experiment, we implemented a questionnaire survey using a 5-point Likert scale. This is a questionnaire used to evaluate the difference in direction up presentation, the pressure presentation, and the comfort of wearing the device. Here are the evaluation results. We obtained high evaluations from many participants for pressure and direction presentation. This suggests that the proposed device is useful for direction presentation. On the other hand, some participants didn't feel much difference in direction. The reason could be that the actuator didn't reach enough to the neck. To solve this problem, the inflatable size of the actuator is increasing and the installation area on the neck. More than half of the users were not satisfied with the wearing comfort. It may be because some users do not feel comfortable wearing the device around their neck, and the presence of the silicone tube may interfere with a comfortable fit. It is necessary to insert a soft cross end to reduce the size of the actuator mechanism. This is the summary. In this study, we created Navichoka, a pressure presentation device using pneumatic actuators to present walking direction to users. This device can be used as a navigation system. Conventional navigation system based on screen display and voice guidance have drawbacks such as encouraging walking and being difficult to use in noisy places. It is suggested that the proposed system overcomes these problems. This device can also be used to receive notification from smartphones, detect obstacles, and work with VR applications. Moreover, the users can use this device as a fashion item because of its natural appearance. Future work, miniaturization, automation, and diversification of tactile patterns. In particular, by automatically controlling the actuators, it is possible to achieve more flexible and complex motion and to continuously simulate the user's neck area. For this purpose, we aim to improve the device by using micro pump and solenoid bubbles. Thank you. This is the conclusion of my presentation. Thank you very much.
Thanks a lot for your presentation. Any questions in the audience? I have one. Actually, to me, it looks like it could be used for maybe dog, or pet directions. Have you considered that?
Sorry.
When you could use this kind of, to me, you could use this kind of device for dog, for, maybe helping the dog to, when you go out with your dog to make him go right or left or, in the right direction.
Oh, with dog?
A dog, a dog, a pet.
Oh, sorry.
Yes.
Sorry, I don't know doggy.
Well, I mean, the pets that you can have as a dog, in English, dog. No, not a human, but a pet that you have.
Pet.
Yes.
Ah. Yes. Maybe this device can use the
Yeah, because you know, dogs, you know, it's difficult sometimes when you go with them out to make them go right or left. They might not know, so you might have this kind of actuator, and they could learn that, you know, when they feel something on the right, they go right, or you know, and then, so just an idea.
Thank you. I haven't considered how to use that, so that will be an issue for the future.
Okay, thank you. So now
Thank
we
you.
are going to the next presentation. Alors, the next one is by Mauro Avila. The title is I Know You Are Looking Into Me, Enabling Eye-Gaze Communication Between Small Children and Parents with Visual Impairments. So I'm going to give you more the co-host, so you will be able to share your screen.
Hello, can you hear me?
Yes, I'm sharing. I'm giving you the right.
Okay.
Just now. So you're going to be able to share. So now you should be able to see a button to share. Go ahead, yeah. Do you see?
Hi, Mom, just give me a second. Can you see my PowerPoint now?
Yes, we see it. It's yes, we see it. So the floor is yours. Good.
Okay, so my start or some minutes or?
Yes, you can start, right?
Okay, thank you very much. Okay, good morning to everybody. My name is Mauro Avila. I am from the group of audiovisual technology from the Technical University of Ilmenau in Germany. I have a pleasure to present you today this research we conduct here entitled I Know You're Looking to Me, Enable the Eye-Gaze Communication Between Small Children and Parents with Visual Impairment. So this work was conducted together with Mrs. Nahme Vasega in our laboratory. Okay. Well, basically, so human has eye-gaze interaction as a basic and instinctive communication activity. So everybody can understand these things from the eyesight or visual point of view. So the communication intention through an eye-gaze interaction is quite natural and common between human beings. But the issue, for example, is for people with visual impairment, this level of communication, of non-verbal communication is restricted, is non-accessible in several levels, so from the basic to the more complex things. So this situation is extended, for example, to within family interaction, natural interactivity. So on the other hand, so in young infant psychology, the eye-gaze interaction is one of the most primal and basic communication interactions that human being has from the youngest ages. So babies start to communicate with the parents through eyesight, even before then start to bubbling or making sounds. Well, so from several years, from several times, so we have seen how computer vision have aided visually impaired people to start to understand this type of communication. Some applications already available for smartphones and other type of assistive technology devices that can allow visually impaired people to, for example, detect smiles or even recognize faces from friends and other known people close to the visually impaired person. So in this point, we arise the concrete questions of how, for example, can this type of available technologies aid visually impaired parents to start to understand eye gaze communication with the small children. We start to address how we can answer these questions, and basically we locate some tools already available for computer vision tools that can allow us to create or detect this type of interaction. The main issue here is we are dealing, one of the part of our questions are small babies also, basically small persons who are not able to speak or to express any concrete intention besides, for example, the eye gaze communication. In this case, we need to find something which allows to detect this type of intention, as I comment, directly without any type of intervention. So we found and modified an eye gaze detection tool, software tool in this case, which can detect directly the direct eye gaze contact with the camera. In this case, the camera is selected to connected to a device which is running the software prototype in this case. So we modify this tool in a way to try to detect this type of interaction. The modification we made was basically related to the directly detection of the eye gaze and the time. We try to address a time window to try to gather, for example, a direct intention from the young infant. In this case, our literature indicate a time frame from more than 5 seconds. We define two time windows in this case to try to detect directly the eye gaze contact. From the first one is a notification in 7 seconds, and the second notification in 15 seconds of direct eye gaze contact detection. Once we have this software prototype running and we need to test it, do all the pandemic situation to try to test this tool directly in the user test would be quite difficult. So we require basically to be in the same room with participants. So the solution we found was basically the important thing in here. So we address 3 participants who was agree to collaborate with us. So we define 3 groups of parents, visually impaired parents with young infants. Those young infants they are able to see. They are basically a normal sight according to medical evaluations, but one of the parents are basically blind. So we found these people, and all the tests was done in remote. So we contact them through a mailing list, and then we send the tool by email and the instructions to configuring them. We try to supervise the configuration also in remote, and we trust in their testimony about the things are running well and well configured. And then we try to basically run the functionality of the test. We try to run the usability, how reliable is the application, and basically how it's run in the equipment that our participants they have in their houses. Then the functionality was tested properly and satisfactorily. So we designed a test where basically there were a casual interaction on tabletop interaction with the blind parent and the young infant. And then we try to define when and how the prototype software detect the eye gaze contact from the baby to the camera in this case. For the situation, the camera was located close to the blind parent's face, for example, in the shoulder, or static in a place close to the face. This setting was basically a little bit bulky, defined like that by the participants, but what basically functional. During the test, the participants decide 3 different times to run the software, and through around 30 minutes in 3 different times as a command. And basically during this period, the software prototype was able to detect direct eye gaze contact from the young infant directly to the parents, in this case, to the camera close, located close to the parent's face. So this proof of concept test was able to define basically how efficient was the software prototype to basically to do what it's designed for, to detect a direct eye gaze, and also to expose the blind parent to the possibility to detect, to know when basically the babies are looking to them. This test was basically successful in the main goal, but basically then we have remote interviews with the parents to get qualitative feedback about the experience about when the software prototype was running. From this qualitative data gathering, we run a technique called content analysis, where we try to pick up concrete sentences, concrete concepts, to know basically which type of qualitative data was most repeated and most present into the data we gather. From that information, so we gather main conclusive points. So we defined that this tool was able to help blind parents to have eye gaze interaction with the children. The emotional impact was very positive to the participants, basically the blind parents in this situation. And basically the parents report an improvement, an increase of their independence, so the autonomy, when they are basically interacting when they're young infants in this case. This is a very early stage of this research. So basically we tried to address a concrete problem which have several other branches, and basically we required a future work, deeper future work, for example, suggested by our participants, and also consider us in our research team, for example, the possibility not only to detect eye gaze contact, also to be able to detect facial expressions from the young infants, as we see in this illustration. For example, could be for the participants declared by them will be very useful, for example, to know when the children are having some satisfaction or disgusting or fear expressions, things where for a blind parent is basically inaccessible. So another possibilities for to know when the children is looking at risky devices, for example, like electric outlets on the walls and things like that. So as I comment, this is a very early stage of this research, and we are expecting, for example, to go further with this thing. So we need to acknowledge, for example, our research group, the audiovisual technique research group of Ilmenau Technical University, and our leader, Professor Alexander Ake, for the possibilities and the hosting of this research for this work. Well, I'm finishing now. Thank you very much for your attention. If you have any questions, please feel free to ask me what you require.
Yeah, thanks a lot for your presentation. It's very motivating work, early work, but then I think your next iterations will be even more important. This is a nice work because it tries also to help disabled people with their relation with their baby. So there are lots of interdisciplinary research actually that are also important there. As you mentioned, the fact that for a baby, it might be very important to have the eye-gaze interaction. So this is a really good project for the good. Any question in the audience? Yeah, so there is, I mean, the co-chair who has joined, who says it's good multidisciplinary. Well, I mean, there are, so, you know, of course you are at the beginning of the research, but so how would you move from the prototype that you have to something which is like working and available for real people? Here we had real people in the test, but I mean, as you can buy as a product for disabled people with visual impairments. So do you think, do you see it as possible in the next years, or it could only remain a project?
Well, basically the main answer could be yes. The pandemic situation basically shrink a lot of the possibilities for this research during the last 1.5 years. So basically the main idea was to be able to run these things mounted in, for example, in a camera with a Raspberry Pi, to give portability and mobility to the solution, to make it more than a software thing, to hardware stuff could be portable and really easy to locate, for example, in a head-mounted thing or shoulder-mounted stuff without a computer, because and basically this is our next step. It was supposed to be one of the steps formerly, but all the situation with to be impossible to test in situ, so limited our possibilities about testing. So basically we need to run these things further, and we hope once, for example, could be possible to get in contact with real users in real life, in person, allow us to do a deeper test of this concept and develop it deeper. One of the things, for example, for this, to make these things in a portable device, small and portable, I should remark, could be possible to I mean, the possibilities could be really many more once we have portability.
Okay, thanks for your presentation. Now we are moving to the next one.
Thank you.
So the next one title is going to be the role of technology in senior co-caregiving support by Jassem Bani Ali. I'm going to give you the co-host role, then you can share your presentation.
Okay, thank you, thank you.
Where are you? Yeah. Okay. Yes, so now you should be able to take the...
Thank you. Let me...
Yes, we are seeing your,
okay.
your slides now. Actually, we see the...
Oh, you see the notes, the presenter
yeah.
view? Okay, let me just share second screen. Okay. Is that better?
Yeah, it's better. Thanks.
Okay. So, hi guys, my name is Jasser Benihani. I'm an MSc student at the University of Manitoba. Today we're going to talk about the role of technology in senior co-caregiving support, a systemic study of senior care mobile applications. For clarification, I'm not the first author for this paper, but Natalie Kapoor is, and she comes from a marketing background, but due to health reasons, she cannot join us today, so I'll be presenting for her. And yep, let's go into it. So in the US, 55.8% of persons over the age of 80 need daily senior care. So senior care is usually expected to be provided or organized by family members. And in 74% of families that provide senior care for their aging members, at least two siblings share caregiving tasks. So 60% of adult children who are actively involved in senior care also work at a paying job. So the need for efficient time-saving ways to organize co-caregiving is more pressing than ever. So while many senior care apps exist, the majority of these apps are designed for organizations that sell services for seniors or to book senior care services. So we begin to look specifically for apps that cater to family co-caregiving organizational needs, such as apps that allow for multiple persons to organize care for a senior. So the inclusion and exclusion criteria for our paper was that the app had to have a co-caregiving properties that allow multiple family members to log into the same account and view activities pertaining to the care of the care recipients, plus one of the other following criteria. The first one, which is designed primarily for senior care or easily adaptable to senior care. The app allows professional service booking for senior care or communication with a professional caregiver, and the services offered are available in the US or Canada. The exclusion was that the apps were not designed to allow for co-caregiving apps. The screening process was a bit difficult, but we managed to do that through search strategies that was built on two concepts: function and population, which is the words scheduling, appointment, planner, geriatric seniors, and older adults. The first selection of keywords had 19 main words: elder care, caregiver, seniors, caretaker, and etc., etc. So we searched in the Google Play Store, searched in both the free and paid categories. The first 50 apps served as a result of each search were screened, and the 19 keywords searched in each of the two categories equaled a subtotal of 38 searches. With 50 app screens per each of the 38 searches, 1,900 apps were initially screened. The four words senior, older adults, gerontology, geriatric were additionally searched in pairing with the following 6 terms: organizing, appointments, scheduling, planner, transport, and scheduler. These were words selected to cover the main functions of senior caregiving apps and thus make sure we are finding them all. The 4 keyword each paired with the 6 other terms resulted in 24 keywords, each searched in both free and paid categories, and they resulted in additional 48 searches. So with 50 apps screened per each, with an additional 48 searches, an extra 2,400 apps were screened. In total, 86 searches were conducted with 50 apps screened per search. So in total, we had 4,300 apps that were screened. So there were a lot of apps that did not meet our inclusion criteria, since Google Play Store has plenty of random apps, to be honest, that appear when we search for caregiving, and we found apps that relate, and when we found apps that relate to senior caregiving, they mostly are for marketing and did not have a lot of features for caregiving. So we ended up with 180 apps that directly cater to senior persons or providers of senior care. And from these 180, 11 of them were designed to facilitate co-caregiving. So we ended up at the end with only 11 applications. Now, 80% of these 11 co-caregiving apps were designed for senior care. 60% allowed for either direct senior care service booking or communication with a professional caregiver through the app, and 55% of the apps were related to the professional senior care service available in Canada or in the US. Now, the discussion and recommendation. There's an increased reliance on technology in the senior and senior care sector, with families increasingly spread across the world and engaged in other jobs in addition to caring for aging loved ones. The phenomena of co-caregiving will arguably continue to expand. So apps that specifically cater to senior care organizers and providers should pay attention to the need for co-caregiving functions. So in total, the study revealed that co-caregiving apps contributing to augmenting the family role in caring for seniors and to enable continuity of careers and social perception. But however, apps that specifically cater to senior care organizing and providers should pay attention to the need for co-caregiving functions as retrieved in the 11 retained apps in our studies, such as the ability for multiple caregivers to log into same account, retrieve and add information about a care recipient for all caregivers to see, and updates and schedule tasks. So these results draw attention to the shortage of digital support for persons engaging in co-caregiving, an opportunity for senior care app creators to develop. Thank you all for listening. If you have any questions, feel free to ask. And yeah, thank you all for listening.
Thanks a lot for your presentation. Any question in the audience? So what are the next? Stop the. It's okay. It's okay. Wait. Alors, okay. Yes. Yes, I was saying. So what are the next steps that you plan? Do you still plan to continue after this research, or you don't know, maybe because you are not the first author?
So I think I have a good idea of what's coming next. I think there will be maybe a prototype of an application that will come next. So it's maybe a universal app for like US and Canada. So it organizes the tasks that we need for to care for seniors, and a good application that will be used hopefully by the government and healthcare workers in the future. So it organizes all the things from care recipients to caretakers and all of the stakeholders that are involved.
Okay. So next steps will be done. Thanks for your contribution. Now we are going to move to the next presentation.
Thank you.
Yes.
Hello, everyone. This is Amin from University of Manitoba. I'll be happy to add a layer to the explanation by Jason. Actually, all what he's explained is great, and he did a good job because Natalie is sick last minute. We apologize for that. So one part that Jason is not aware of, but what he said is really reliable. Actually, we are now conducting surveys and interviews with healthcare professionals and governments in 2 provinces in Canada and 3 states in the US, in the southern USA. And the idea is that, just I wanted to share that, is we flip the process. So we start collecting data with people, with the governments to understand their need, and then we apply what we learn from that into the developments of the app. So the concept of caregiving is not existing yet in the existing app. So we look forward to develop that. And what Jason presented is the very first like a capstone to it, the first step, the first ideation piece. So next step is to develop it in the next month, and then validate in 3 states in the US and 2 provinces in Canada.
Okay, good.
So much.
Great. Okay. Next presentation. So the title is Augmented Percussionists. A new musical experience by fusion of melody, morphing, and electrical muscle stimulation. And the presenter is...
yes, this is me.
Yeah, so you are... I don't know.
Okay.
So you are Hiroya?
Yes, I'm Hiroya Miura.
Yes, okay. So I give you the... you already have the...
Yes.
Okay, you already have the right. Okay, so that's good. So you can, the floor is yours.
Okay. Good evening, everyone. My name is Hiroya Miura of Riken in Japan. Today, I'd like to talk about augmented percussionists, a new musical experience by fusion of melody morphing and electrical muscle stimulation. The fusion of music information processing and human physical function will allow new musical experience to be created. We developed an interactive music system called Augmented Percussionists, which provides users with the experience of playing an automatic musical performance. The system converts music into EMS and controls the body movement of multiple people with devices attached to their hands and feet to realize the performance. The augmented percussionist is a system that enables melodies to be manipulated with the melody morphing method. Variations of melodies are composed on the basis of the generative theory of tonal music, GTTM, whereby switching the melody segment keeps the overall structure of the melody and only changes the ornamentation. Because of this, the user can control the performance by performing a melody. Okay, now please watch the video about the system we developed.
We developed an interactive music system called Augmented Percussionists, which provides users with the experience of conducting a musical performance. This system converts music arranged using melody morphing into electrical muscle stimulation to control the body movements of multiple performers via devices attached to the performer's limbs. The Augmented Percussionist uses an EMS system to establish control over simple movements, such as snapping wrist joints and flexing elbow joints of performer. The EMS system includes a device that generates electrical stimulation by using an Arduino circuit, personal computer, direct current stabilized power supply, and electrode pads. This EMS system can synchronize the body movements of many people by controlling multiple EMS generators in an integrated manner. This makes it possible to play various types of ensembles. We developed a graphical user interface that enables anyone to easily manipulate melodies and performers. The operation method is as follows. First, by selecting two songs and pressing the Generate Music button, multiple melodies obtained from melody morphing are generated. Second, select a song to play from the obtained melodies. And finally, electrical stimulation is generated and sent to the electrodes corresponding to each sound. We determined the correct electrode pad position to reproduce the movements of each performer by considering the movement of the muscles. The handball players could play the main melody generated from melody morphing in full control. In addition, the drummer could play the corresponding 4 beats with full control by reading the tempo information of the song being played. And the dancer proceed rhythm dance as he dance, while keeping the rhythm in sync with the other participants. We will pursue a new style of musical experience by fusing music information processing and human physical functions.
And this video is full picture of our research. The augmented percussionist, which enables the user to manipulate music freely, uses a melody morphing method that we have constructed on the basis of melody manipulating using time span tree of GTTM. We believe that computers that deeply understand music must be developed to achieve a composition support system that enables various musical operations. Therefore, we have been researching and developing systems based on GTTM to understand deeply music structure. And the time span tree, which is the deep structure obtained as a result of GTTM analysis, structurally shows the relationship between the important notes. Finally, we can realize melody morphing, which generates an intermediate melody from two input melodies by using time span tree. Now, I talk about the EMS system. The augmented percussionist uses electrical muscle stimulation to establish control over simple movement of multiple people. As shown in that video, this EMS system can synchronize the body movement of many people by controlling multiple EMS generators in an integrated manner. The augmented percussionist is ideal for the automatic playing of ensemble percussion. It can convert music arranged the melody morphing method into EMS and control the body movements of multiple performers, such as dancers and musicians, by devices attached to the performer's hands and feet. In addition, to enable anyone to easily manipulate melodies, we have developed a graphical user interface that makes it possible to replace part of melodies. Thereby, the user can control performance by freely manipulating the melodies. The performance using this system lasted for about 5 minutes, and we confirmed that the system is effective by synchronizing the playing of the melody by using melody morphing method and controlling performance movements. My conclusion is the following points. We developed an interactive music system called the Augmented Percussionist, which provides users with the experience of playing an automatic musical performance. We will pursue a new style of musical experience by fusing music information processing and human physical functions. And we plan to construct a system that enables more complex instrumental performance. This is all for my presentation. Thank you for listening.
Okay, thank you for your contribution. We have one question in the chat. So there was previous work called stimulated percussion. The question is, so what is the new, the novel contribution compared to this previous work?
The contribution of this research is fusion of music information processing and human physical function. I think this is my contribution of this research.
Yeah, so it seems to be more like a team. It's multiple persons, and before maybe it was like only one person, right? Here you have a fusion of a group of people also executing the performance, I guess. Okay, so then another question. So did you have feedback from an ethical committee for this work? Ethics.
Sorry, please.
Did you have did you have a feedback from guidance from an ethics committee?
No, still now I don't have feedback.
Yeah,
so,
okay. I mean, I think for this one, maybe I can, usually when you do some research that involve sensitive information or maybe medical aspects, you should ask your ethical committee. But here, I mean, maybe you didn't. I think for music, to me, in this one, doesn't seem really of major importance.
Yes, okay.
For example, in the Navi choker one, yes, there was also this question because it's around the neck, and then maybe sometimes, although it's not very strong, you could have some injuries around the neck, or for breathing or blocking the blood is not so might be. So I'm not sure if they had some feedback from the ethical committee. Also, usually, as I said, I mentioned that the research could maybe fit for dogs, but for humans, that's true. Also, it's a bit surprising to use. But I mean, here in your case for music, I'm not sure there is. To me, I've been involved previously in some ethical questions. Don't see a major importance here. Okay. So, any other questions? No. So we are going to the last short presentation. So it's about users' perspectives on haptic technology used in hand rehabilitation. And again, it's JSM, but this time with as the first author. So JSM, you can, I think you can share your screen again.
Hello. Okay, let me share my screen. Okay, can you see the slideshow?
Yes.
Okay, perfect. So hi guys, hi again. My name is Jasper Benhani. I'm an MSc student at the University of Manitoba. I am under supervision of Dr. Amin Choku, and today we're going to speak about the user's perspective on haptic technology use in hand rehabilitation. And yeah, a little background. According to the WHO, 50 million people suffer from stroke every year, and this number is anticipated to rise in the next 10 years. And more than half of stroke patients suffer from loss of function on their affected limb. And from my background, I'm personally seeing patients get informed that they cannot use their hand at the moment due to neuronal damage. Now, the current solution to enhance hand function is neuroplasticity. Now, not so long ago, many scientists believed that the brain did not change after childhood, as if it's hardwired, but recent advances in the last decade now tell us that this is simply not true. The brain can change and will do, and does throughout our lives. It is adaptable. And neuroscientists call this neuroplasticity. Think of your brain as roadways, and there are billions of them. And these roads are being used once you have done anything from thinking to when you raise your finger. And every time we use these roads, they are being strengthened. And it becomes easier for us to travel these roads. So if we want to learn a new task, we start carving a new road and we keep traveling. And if we keep traveling that road, our brain begins to use this pathway more. And this new way of doing this task becomes second nature to us. Now, this process of rewiring your brain by forming new connections is called, as we said before, neuroplasticity. So the basic idea is that we want the patient to do a high repetition of tasks so he could enhance his hand function. Now, scientists leaned into using robotics since implementing a clinician to every stroke patient is costly and time consuming. And some studies even reported better outcome measures when using these robots. So in order to make the experience more realistic while using these rehabilitation robots, haptic technology was implemented. So this brings us back to our questions: why haptic feedback is needed. Why haptic feedback is needed is because we want to make the interaction between the user and the robot more realistic. So a little background about haptics. Haptics is derived from the Greek word hapticus, which means being able to come into contact. And haptic is a technology that registers touch by applying vibration, motion, or forces to the user while interacting with a robotic device. the literature on the use of haptics in robots designed for upper extremity rehabilitation in stroke patients spans over the last 20 decades. So the most well-known examples of haptics are probably the vibration on a mobile phone or the rumble in a game controller, but there are actually a huge variety of applications. Today we are going to speak specifically on rehabilitation robots that uses haptic technology. So, research on rehabilitation robots focuses on clinical results without addressing user perspective. Patient safety using these devices might be a concern because of the variation of functional and cognitive levels between patients. Hence, developers need to design a versatile haptic robot to meet the patient's functional level from severe to mild cases, since robots right now are only mainly to mild cases, thus not enabling a personalized rehabilitation treatment. So this paper aims to explore the literature that includes user perspectives on haptic in hand rehabilitation. But why we are interested in haptics in the first place in hand rehabilitation? Because vibrations that come from using haptic robots constitute a safety issue that might increase pain, decline the treatment progress, or decrease motivation. Moreover, patients' decreased functional levels can make it hard for them to reach the safety switches on these devices. So perception of danger or decreased adherence to treatment might compromise the success of the therapy. So patient acceptability is therefore crucial to the success of the therapy. Uh, from our methodology, we extracted the data that were included articles. A scoping review was carried out based on the ARCSI anomaly framework. A total of 3,136 were generated from the research and Medline, Embase, Sinhal, Cochrane, Scopes, and Web of Science. After removing duplicates and screening titles and abstracts, full text articles of 516 articles were retrieved. Of those, a total of 42 peer-reviewed articles were included in the study. Articles were published between 2001 and 2018 with an average of 2.6 plus and minus 1.8 articles per year. To be included, articles had to be written in English or French, involve participants diagnosed with stroke, used a rehabilitation robot that used haptic technology, examine the effects of haptics on hand rehabilitation. Studies that reporting on technology development and validation or involving technology used an assistive device were excluded. So our scoping review focused on qualitative/quantitative data that reflected user perspective, explored through questionnaire self-reports and interviews and scales. We extracted the data from the included articles that is related or close to the following aspects: perception of motor function, motivation, perception of their results, the effectiveness of the robot, comfort, duration, and etc. etc. We determined that these aspects are critical things to look for when using a new robotic device. Now, out of the 42 results, 81 or 34 papers had researched quantitative clinical data only, and 8 papers had used qualitative methods, questionnaires, self-reports, and scales. The 8 papers that researched qualitative data, 6 of them mentioned perception of motor function, and 5 different papers collected ease of use, comfort, satisfaction, interest, motivation, and perception of results from the users of the rehabilitation robot. But sadly, none of the papers included users' feedback when using haptic technology and haptic robots. So nothing was specifically written about the haptic technology itself. Now, the results indicate that the clinical research should collect qualitative and quantitative user perspective data about haptic and rehabilitation robot as a part of their methodology, and there was no information on how haptic specifically affected the interaction between the patient and the robot. And surprisingly, clinicians' perspectives were not addressed among the papers included in this scoping review. So there are significant safety concerns since rehabilitation robots, although used for patients, can emit high force outputs. Also, users of the robot suffer from decreased motor and functional levels, which creates a risk when using these devices. So in conclusion, this scoping review stresses the need for including further user perspective evaluation in the studies on haptic technology and in-hand rehabilitation. The reason why we are really interested in haptics right now, because we are working on iManus robot, telerehab robot that is ongoing work with Tactile Robotics and the University of Manitoba with Dr. Choku. Initial results was presented by Ali Madahi last year. So we're going to present a short video of what it is. Now this is the iManus telerehab robot. And since I come from a clinical background, I will help with the clinical piece of this robot. We are planning to implement haptics in this device because right now we can only measure range of motion for the wrist and the
video. We don't see
you can't.
the video.
Oh, sorry. Oh, okay. Sorry. So this is the iManus by Tactile Robotics and University of Manitoba.
Full screen, please. Full screen.
Yeah, and then the sound is this sound, no? Because we don't.
There is sound, but it's not.
Should play.
Okay, 1 second. Sorry for I don't know why the presentation does not play in PowerPoint. Okay, so this is the iManus by Tactile Robotics, and as I said before, this is a telerehab hand robot, and this is ongoing work with Tactile Robotics and the University of Manitoba with Dr. Choku, and Ali Madahi presented like initial results from last year. And I'm a physical therapist, so I come from a clinical background. I will help with the clinical piece of this robot. Right now, it's measuring range of motion of the wrist and metacarpophalangeal joints, which is the fingers. And we are planning to implement haptics in the future, so it could provide a more immersive interaction and a more realistic interaction with the patient. And sadly, from this paper, we did not get a lot of information on how we could improve the haptics. In our project, but we are planning to conduct multiple case studies in the future on patients from Canada, and yeah, hopefully we'll do an improved version, since COVID this year had a lot of obstacles that came our way. But hopefully we have the second version that will be involved in haptics and will be more user friendly to the patient, and we'll start distributing it to patients, and we can do some clinical trials on them. Thank you all for listening. Sorry for these technical issues at the end. If you have any answers, if you have any questions, feel free to shoot them forward. And yep, thank you.
Thanks for your presentation. So any questions? So we have some feedback here in the chat. Okay. Yes, well, there was a comment about your name, I think, appearing somewhere. So this work, so it's you mean this is also an interdisciplinary work, right? You are, yeah. You said you are from the more like the which master did you do before, or which studies did you do before? You said.
I'm a physical therapist, so
physical therapist, yes. So and then you are also interacting with IT students,
yeah,
and researchers, right?
Yeah, right now I'm working with engineers in tactile robotics, and under the lab also with Dr. Amin and the rehabilitation technologies lab, and yeah, I'll be providing the clinical piece for this device, but it's mainly not for physical therapists, it's also for OT, so it's multidisciplinary, as you said.
Yeah, I think so that this is important. I would encourage researchers from information technology or robotics to really also from the start try to work with medical researchers and physiotherapists. Why? Because when we talk about these extensions. In the long term, they can create a lot of issues, and this is much better to take that into account at the beginning. Also, the ethical questions, we had several questions around these questions of ethics, and they are more and more important. People they like new technologies, but they also want that these new technologies have good ethics, from an environmental point of view, but also here from the well-being point of view in the long term.
Yeah.
Okay, so that was the last presentation that we had for today. So that concludes the submissions for the 2021 Augmented Human International Conference. And now we are going to move to the award ceremony. So let me add my, wait, I shouldn't share the results at the beginning. So let me just change off slide. Okay. So we'll share now. Okay, so thanks to all presenters today for the good presentations and good contributions to the Augmented Human Research International Conference. And we also thank you, the people who attended as audience for this conference. We are going to, as I said, for the people who agreed, we are going to publish these videos on the social channels of Augmented Human. And after the awards, actually, we are going to have good news about the location for Augmented Human 2022. And hopefully this time we will be able to do it physically, not only remotely. So we had different categories of papers. At the beginning of this day, we had more longer presentations because they were longer papers. In the proceedings, you can see that you have different types of papers and contributions. The ACM is going to publish the final version soon in the ACM digital library. And so based on the scores that each paper got when they were evaluated during the reviews, then we selected the one that got the best scores. And for the long papers, the best long paper, so award for Augmented Human 2021, is manipulating virtual objects in augmented reality using a new ball-shaped input device. So presented by Bastian Schmeyer, and with co-authors Jan-Patrick Koppeds, Burks Kortz, and Nicole Jo-Schems. So congratulations to you. I think Bastian is still here.
Yes, yeah.
So we will, we will send you the certificate. Then we had a shorter contribution, but still interesting, as we saw during the presentations. And the best short paper then is the ink slime that we saw demonstrated also during today's presentation. And so I think this one was presented by Ziyu Ding, right?
Oh yeah, I'm here.
Yes.
Thank you so much.
Yeah, so congratulations to you. We'll send you also the official certificate, and we will put it on the Augmented Human social channels. And finally, so we had also some poster papers, but we couldn't really have big posters, so they were presented as well. And we saw this augmented percussionist, and they got also good scores. So they got the best poster paper award. So we've got best long paper award, best short paper award, and best poster paper award. So congratulations to you, and anyway, congratulations to the others. It's good to have a paper in the ACM digital library. The ACM is well known, so it's always a good achievement. And then we have to select. We have only one best among each categories. It doesn't mean that your contribution was not of good quality. It was accepted. So congratulations anyway. So now we have this question, so where maybe we meet in 2022 physically, hopefully, because the coronavirus will be eradicated thanks to the vaccines that are spreading around the world. I think Professor Choukou has something to say about that, right?
Yes. So, yeah. Can you see me, hear me?
Yes.
Yep. So hi again, and thanks so much everyone for this great day. I hope you enjoyed the great keynote by Dr. Sinan, and I really enjoyed most of your presentation. I have missed some personally because of time changes, but I will review all of them later in the Zoom link. So next year, conference will be here in Winnipeg, like last year. I'll be very happy to host that as part of the College of Rehabilitation Sciences, University of Manitoba. I hope we can make it physically. And if not, then we will make another online event. So please hang in there. I promise to make as best as I can and to be very adaptive. We are updating the website soon. I'll be communicating about that. And I hope to see you all there. Please encourage all your communities to present there. And we would be very happy to host you, either physically or online. And also, I would like to apologize a little bit about the delays in the processing. Actually, those delays are run by updates in the ACM system. So thanks so much for your patience and interactions with us. Please believe us, we are really working hard on that. Just the system is completely changing. So, so we tried our best to be on time. So I look forward to your presentation next year. I'll be very happy to host you again. And again, congratulations for all the presentation. It's really a great day. So look forward to see you next year in May 26 and 27. We put that at the end of the weekend. So at the end of the week. So I hope we see physically, and then you enjoy a little bit of Canada on the weekend time and go back to your country by Monday. This is what we hope for, and we will plan accordingly. Thanks so much again.
Okay, thanks, Professor Choukou. Great. We are really looking forward to it. And hopefully, I mean, clearly it should be possible. Let's be positive, right? Okay, great. Congratulations again to everybody. So we will meet hopefully next year in Canada then.
Yeah, you are welcome.
Thanks, everybody. We stop now, and we will hopefully meet next year. Bye-bye.
Thanks so much.
Bye-bye. Take care.
Thank you very much.
Bye-bye.
Thank you. Bye-bye. Take care.